So hi guys, Happy New Year to all Form 4, 20 and 21. So now we're going to talk about the second chapter in Form 4 Kssm syllabus, which is the structure of atom. So we start off with the first subtopic, which is matter. So now, what is matter? So matter is easy to be simplified as matter is anything that has mass and can occupy space. So anything, any object, any form, any molecule that has mass and also can occupy space are considered as matter. And matter would exist in three states, which are solid, liquid, and gas. So it can be seen physically as a solid, as a liquid, and as a gas. And each of the states of matter will portray a different characteristic that we'll talk about later. Stay tuned. So as I've mentioned before, there are three states of matter, which are solid, liquid, and gas. And among the three of them, it can be interchanged. So meaning that solid can turn into liquid, and liquid can turn into gas, and vice versa. So if solid turns into liquid, that is a process where we call as melting. Liquid to gas is what we call as boiling, or we can also say evaporation. Okay, if gas to liquid, that is what we call as condensation. Liquid to solid is what we call as freezing. And there are two more additional changes or process that change the state of matter. From solid to gas is what we call as sublimation. And also from gas to solid is also sublimation. So both of them has the same name but different way, we could say. So if solid to gas is sublimation, gas to solid is also sublimation. Okay? Therefore, this is how we go through all the process and how we heat or cool stuff. Stay tuned for the graphs. So these are the arrangement of the states of matter. So this is the solid arrangement, this is the liquid arrangement, and this is the gas arrangement. Okay? So now we need to describe the characteristic of these states of matter. So what can we see in solid? First, it is closely packed. What does it mean by closely packed? These are what we call as atoms, or we can just, as what we call it, as commonly being called, it is what we call as a particle. Okay, so this is a particle. So we have 1 particle, 2 particle, 3, 4, 5, 6, 7, 8, 9, for example. So now, from 1 to 9 particle, all of them are basically co-join each other. So they are not stick to each other, but they are basically touch and closely packed to each other. So one characteristic, they are closely packed. Therefore, when two things or more are closely packed and basically attracted to each other, what force would it need? Of course, it needs a force that we call as a force of attraction. Therefore, in solid, since it is basically closely packed and very, very close to each other, the force of attraction between the particles are high. So the force of attraction between the particle is high. Okay, and then the third one is when the force of attraction is high, basically they are sticking or attracting to each other. They can't move around and just go this way and this way. Therefore, it doesn't move as much. It just basically vibrate and rotate. Therefore, the kinetic energy of the particle is the lowest among the three. Okay? So we're going to talk about liquid later. Okay, so now we're going to talk about liquid. So when we're talking about liquid, as we can see, it is still closely packed to each other, but it cannot defeat this because, as we know, solid has the most closely packed particles among all three. So liquid, we can see that it is loosely packed to each other. So it is loosely packed but not as loose as gas and not as close as solid. And for the force of attraction, it has a higher force of attraction than gas but lower force of attraction than solid. Okay? And another one, it has a higher kinetic energy than solid but a lower kinetic energy than gas. Meaning that, like I said, it is closely packed, it is closer packed than gas, therefore the force of attraction is higher than gas, but then the force of attraction is lower than solid because it's not as closely packed as solid. It has a higher kinetic energy than solid because, as you can see, there are spaces in between, so it can move freely rather than solid where it couldn't move freely. But then, since you see in the gas there is ample of spaces in between the particle, therefore it cannot defeat the kinetic energy of gas, therefore it has a lower kinetic energy to be compared to gas. Okay, next we're going to talk about gas. Okay, now for gas it's quite simple. So it is very loosely packed, it has a low force of attraction among all three, and it has the highest kinetic energy among all three. Okay, so next we're going to talk about the heating and cooling curve graph that I mentioned before. Stay tuned. So now we're going to talk about the melting and freezing curve. So these are the curves that you would expect whenever you're doing an experiment of melting and freezing. So melting, what is the process of melting that we mentioned just now? So melting is a process where you take a solid, you add heat, and it becomes a liquid. And what is freezing? You take a liquid, you cool it, and then it becomes a solid. So, like I said, melting a solid, you heat it, so temperature rise. So this is melting. And freezing, you take a liquid, you cool it, so temperature reduce. So this is freezing curve. Therefore, when you have melting curve, as you can see, there is a moment where there is a constant temperature in both, in melting and freezing. Okay, I will explain later why, but now, just for the knowledge, when the temperature is constant, that exact temperature is actually your melting point. So that is the melting point. That is the temperature where from a solid turns into a liquid. So as long as it doesn't reach that temperature, it will not change in state. Okay, what about this? So at the temperature where it is momentarily constant, that exact temperature is also the freezing point. So for example, if we are handling water, so the melting point of water, so this is ice, and it slowly turns into water once it reaches B, where the temperature would be hypothetically, which should be 0 degrees Celsius. And if you take water and you cool it, it needs to reach 0 degrees Celsius as well to start turning into ice cubes. Okay, so now we're going to talk about what is A, B, C, D, and what is A, B, C, D here as well. So it's quite simple here. So as you can see, from A to B in the melting curve, what is increased? So there is increase in temperature. When there is increase in temperature, this is what we say solid state. So at A, for example, we're using ice. So this is still ice, but then it hasn't reached 0 degrees Celsius, so it was still continuously being ice cubes until to the point of B, where it reaches 0, then only it starts turning into liquid. Therefore, the whole journey of A and B is only solid. So there's only solid exists in between A and B. In between B and C is another story. So wait, we're going to talk about A and B first. So now, A and B there is increase in temperature, and A and B, it only exists in solid. Only solid exists. And another thing that we need to remember, when there is increase in temperature, just imagine if I put you guys in a hot water. So what you guys are going to do? So if there is a hot water or hot pot, you guys touch it, you will straight away pull your hand away from it, right? Therefore, when higher in temperature, higher in the movement of particle, or we could say as the kinetic energy of the particle. So we can see that if this is the particle closely packed as solid, when we heat it up, it will move to an extent, it will turn into water. And when that water, it will still move to turn into gas. As the distance between the particle increases, the solidity reduces, it can turn into liquid, and if the process continues, it will become gas. Okay, so now 3 things to remember in A and B. There is increase in temperature, only solid exists, and there is increase in kinetic energy of the particle. Okay, got it. So now B and C is the bit of crucial part. So when we are talking about B and C, what can we say? There is no change. There is no change in temperature, but there is changes in the states of matter. So now as we can say, A to B there's only solid, but B to C is when solid and liquid are coexisting to each other. So at this moment, B to C, if you check onto your experiment, there are ice cube and water together. So this is when there is solid and liquid. So there is changes in the states of matter. There is no change in temperature, but there is changes in the states of matter. So where you can see solid and liquid coexisting together in this moment. Okay, now why does that happen? So why does that happen is the main question here. So let me explain. So now you heat up a thing. It's supposed to increase in temperature, right? But you need to remember, when the particle is moving, we are not just talking about kinetic energy when we talk about solid just now. So what does solid has? It has a very low kinetic energy, which is increased by the temperature, but it also has a strong force of attraction. So how would we break the force of attraction? By using the energy that is being given to the system, which is given to the particle by the heat, because we heat it up. So you burn the naphthalene receives the heat from the fire, and then the heat from the fire is in the form of energy. So the naphthalene will use that energy to break the bond, or we could say to break the force of attraction between their particles, to make them into water. So to make them into liquid naphthalene. Therefore, since there is changes in states of matter, therefore we could say that the energy released by the surrounding is absorbed. So the energy released by the surrounding, which is the fire, is absorbed by the particle to overcome the force of attraction. Okay, we'll talk more in class. Okay, now we're going to talk about freezing point. Stay tuned. Now freezing point or freezing curve. So freezing curve, there's also A to B. As we can see, from A to B, there is drop in temperature. Of course, drop in temperature, drop in kinetic energy. And drop in kinetic energy, does the states of matter differ? No. So in A to B, it is still liquid. It is still in liquid form, so it wouldn't change. Okay? But now, B to C, same story here. There is a momentarily constant temperature. Therefore, when B to C, like we say, constant temperature, the states of matter changes. States of matter change And why is that? That is the big question again. So why now we understand here that the fire, the energy, the heat energy from the fire is being used to overcome the bond. What about this one? So now, like we say, we put it in a fridge. So it is cold, right? Now, when we are breaking a bond, now here, when we are breaking the force of attraction, you need energy. You absorb energy to break the force of attraction. Here, from less force of attraction, you are increasing the force of attraction. You need energy. So now, you already have the energy, but you want to slow them down. So when you have higher energy, or basically you have high kinetic energy, you want to lower them down. So when you lower them down, this particle need to release the energy elsewhere. So when they release the energy elsewhere, they reduce in energy, and that bring down them together, and their force of attraction will increase as they come closer to each other. Therefore, we can see that the temperature remain constant because the formation of bond, we could say the bond, meaning that there is a bond, or we could say interaction between the particle. The formation of interaction between the particle, is release energy to the surrounding. And yeah, it's a bit confusing there. Why? Now we are saying that when the force, or when the bond, or when we could say when the interaction is being formed, so when these particles are being closer to each other, they release energy. So when they release energy, isn't it going to increase the temperature? Yeah, it sure does. But you need to remember, you are cooling something. When you are cooling something, you are putting it in a refrigerator, for example, or you put it in ice. So now when you put something in ice or somewhere that is cooler, the surrounding is absorbing the energy that you are emitting. So the particle are releasing the energy, the ice or the surrounding is absorbing it. So you release and someone absorb. So there is no excess, or there is no actually spike in temperature here. So nothing is being excessive. So actually we could say in simple form, when the interaction or when the bond between the particle is formed, they release energy, and the energy is being absorbed by the surrounding. Therefore, there is no increase in temperature. Okay? Now we're going to talk about C and D. Like C and D, sorry, I also forgot about the C and D here. Okay, just as a short note, C and D, increase in temperature, no change in the states of matter, because now all would be existed in solid, in a liquid form, in liquid form. Whereas this one, there is a drop in temperature, no change in states of matter, but everything is in solid state. Okay? So we're going to talk about the atom now, which is the best part. Okay, so now before we delve into atoms, we're going to talk about the types of matter. There is two main types of matter, which is elements and compound. You might be wondering, where does the mixture go? So the mixture is basically elements, they are just physically mixed together. So they are basically still elements. So now, elements exist in two forms, which are atoms and also molecule. Okay. Compound also exists in two forms, which are molecule and ions. Okay. You might be wondering, how come does molecule can exist as an element or as a compound? So if we're talking about molecule that exists as an element, we might be talking about oxygen. Because why? It is a molecule because there are two oxygen being bonded to each other. But we don't classify them as a compound because both of them are oxygen. Both of them of the same atom. We'll talk about it later in few chapters ahead. Okay, but if we're talking about molecules that are in compound state, so we might be talking about carbon dioxide. So there is carbon and oxygen. So there are two different atoms being bonded to each other. So when they are being bonded to each other, they form a compound because they are two different atoms. While this is two same atoms, so we still classify this as an element, whereas this as a compound. Well, ions, we're going to talk about later, but ions is when an atom changes its configuration and just form an ionic bond. Okay, so later we're going to talk about atom, what is in atom, how to draw an atom, and what is the history of atom. Okay, now before we talk about atoms, so we're going to talk a bit of history of how we discover the atoms that we know now. So these are the 5 famous names that are very popular in the structure of atom. So Sir John Dalton giving a postulate that a particle is sphere. That's it. So that was his postulate and that was his study. So John Dalton said that a particle is basically a sphere. J.J. Thomson continued the study where it is basically a sphere where there is negatively charged particles, or we could say they are negative charge, or we call them as electron, moving around and inside the sphere. Ernest Rutherford extend the study to saying that there is negative charge moving around, but there is a positive charge right in the middle. Okay, so Niels Bohr and James Chadwick had a completely different, and it was a bit a notch above. So why? Because Niels Bohr discovered something a bit different. So Niels Bohr discovered that the positively charged is situated in the middle, or we could say the nucleus. So, well, Ernest Rutherford also said that the positive charge is acting as a nucleus. But Niels Bohr also postulated that there is an existing shells, or we could call them as orbits. So basically, Ernest Rutherford said that the electrons or the negative charge is moving around and a positive charge is right in the middle. While Niels Bohr discovered that the positive charge is in the middle, but the negatively charged is moving around, but it is moving in a very uniform orbital motion. And James Chadwick, to finish it up, in the middle it says it's the nucleus, not only the positive charge, but there is what we call as proton, which is the one that carry the positive charge, and also neutron. Well, it's just say that he mentioned that in the middle it is positive and a neutral charge right at the nucleus, and then there are shells, or we could say as orbits of the electron, and there are electrons moving around in the orbital motion manner. So this is how the journey and the knowledge evolve and being discovered above discovery and above discovery and above discovery, when now actually our atom, there is a nucleus where there is proton and neutron. There are shells, which are the orbits of the electron moving around. We'll talk about it later in the next clip. Stay tuned. So this is an example of an atom. So in the middle, this is what we call as the nucleus. And the nucleus consists of 2 different subatomic particles, which are proton and neutron. The one that I mark as X is the one that we call electron. And all 3 of these, which are electron, proton, and neutron, is what we call as the subatomic particles. Okay? So, what are the difference between the 3? So, electron is the one that carries the negative charge. Proton is the one that carries positive charge. And neutron is the one that carries the neutral charge. Okay? relatively, the mass of proton is 1 unit, the mass of neutron is also 1 unit, but the mass of electron is approximately 0.0005 unit. So, to be compared to electron and proton, they have a very vast and ample difference. So, it's 1 to 0.0005. Okay? So, now, we are going to talk about how the structure of atom is being, can we say, and how to describe it. Okay, so now we're going to talk through about how the structure of atom is and how to state the electron arrangement. So now, we have the first shell, second shell, and the third shell, right? So, in the first shell, there is 1, 2. There are 2 electrons. In the second shell, there are 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons. In the third shell, there are 1, 2, and 3. 3 electrons. Therefore, when we are requested to write the electron arrangement, the electron arrangement would be 2.8.3. Why do we dot H? That is to signify the 2 is from the first shell, the 8 is from the second shell, and the 3 is from the third shell. Okay? So this is how we describe. Therefore, now, when we mention about nucleus, we mention about proton, we mention about neutron, and we mention about electron, there are numbers that we're playing with. So, in certain atom, there are number of electron. So, when there is number of electron, there is also the number of neutron and also proton. Therefore, in the nucleus, we have something called nucleon number. Nucleon number is equals to proton added with neutron. So, nucleon number is the sum of proton and neutron together. Okay? And electron is basically electron number. So, what is the number of electron? 2 plus 8 plus 3. So, there is 13 electron in this atom. Okay? So, next we're going to talk about how an atom or another atom has the same number of proton, but it is called differently. Okay, like I've mentioned, in some cases, there are 2 atoms, for example, carbon 12 and carbon 14. Okay, so both of them are carbons. But why this is called as carbon 12 and why this is called as carbon 14? So the difference between them is the nucleon number. So the nucleon number for carbon 12 is 12 and the nucleon number for carbon 14 is 14. Okay, so when we were to write, we need to know how many proton number are they. So as a normal carbon atom, we have 12 electron, we have 6 electron, 6 proton, and 6 neutron. So when there is 6 electron and 6 proton and 6 neutron, 6 plus 6 would be 12 nucleon, where we just take this value, which is proton plus neutron. So 6 proton plus 6 neutron is 12 nucleon. That is what carbon 12 is all about. So carbon 12, there is 6 proton and 6 neutron. But for the case of carbon 14, the proton is still 6. But the neutron is now 8. So see, the protons must be the same, but the neutron is different. Therefore, you have 2 same but different atoms. So these atoms are what we call as isotopes. So isotopes are two or more atoms that has the same proton number but different neutron number, which make different nucleon number. So now, as an example, when you have carbon 14 and carbon 12, which we mentioned of isotopes, right? So now, we are going to talk about the relative mass of atom. Why do we need this? Okay, now, if you find a carbon, you get a carbon, so it could be carbon 14, it could be carbon 12, it could be carbon 13, well, we never know. So now, when we have this kind of situation, what is the real mass of carbon that we're talking? Is it 14 or is it 12? So that is when we need to calculate the relative mass of atom. And the formula is the total of percentage of the isotopes times by the mass of the atom of the isotope divided by 100. Okay, so this is just an example. It's not a real situation, but just for the sake of our discussion today. So now, what is the percentage of the carbon 14 isotope? So it is 15 times by the mass is 14. Okay, plus 85 times 12, and you divide it by 100, and the answer you get would be the relative mass of atom, or simply say it's basically the average mass of carbon per se. Okay, so disclaimer, this video is just a summary of the topic. It's not a full revised topic.